Now, for all supersonics, one of the advantages is that the equations used are often quite straightforward. And this is a nice one for estimating the coefficient of pressure on the surface of a supersonic wing, particularly if it's quite flat in that area. So basically what delta is the angle of the local surface to the flow. So the angle of the actual vehicle, so whether it's the wing or the tail, to the local surface. So angle of the flow to the local surface. As that changes, delta changes. So therefore, if you can work out what angle your aircraft or wing has locally, so you have a number of deltas over the surface, you can actually work out at each of those points what CP is. And basically this is the free stream Mach number. So this is the Mach number we're travelling at. That's an awful lot easier than many of the other ways that we do of calculating pressure. It is an approximation, but it's not a bad approximation, particularly for thin vehicles and particularly ones that are not so curved, if you like, much more flat, faceted type vehicles like stealth. But it's a very fast way to get a good value. Right, so swept wings in supersonic flight. Okay, now what we've got here is that we've got a vehicle in the way which is producing shock. Now, what you can do in some senses is if it's very, very thin and very, very sharp, theoretically you can have a Mach wave but not a shock wave if it's very, very thin. In reality, that doesn't really work, and we tend to always see a shock wave. Now, what the whole point of this is, let's have a look. When the component of free stream velocity perpendicular to the leading edge is less than the local speed of sound. So if we're starting to sweep things back, even in a supersonic flow, if you actually say, well, what is the angle that this is at? So the flow comes along, but it's at an actual angle to the way that the wing, because the wing has been brought back on sweep. It may well be that crossing over the wing according to, if you like, perpendicular to the sweep, is not a supersonic part. And if that's the case, you get a Mach wave. Okay, a Mach cone, as distinct from the shock wave. So therefore, if we've got a straight wing, it will always produce shock waves. We can sweep it back and actually weaken the shock wave until we could actually make it disappear. As I said, in reality what tends to happen is because of the leading edge that we have on aircraft tends to be round, then generally we always have a shock wave present. But theoretically, if you could make it very, very sharp, you could sweep it back and remove this problem. There's mu, sine of 1 on the Mach number, fair enough. And with sweep for supersonic, you can see what we've got here. This is the area which has actually been created, shall we say, by the Mach cone, this part here, or this one here. And the aim of supersonics is you want to sweep it back so it goes inside that. If it's outside, you've got very, very, very large wave drag. If you bring it inside, so the disturbed flow is outside your vehicle and you're tucked in nice inside, you'll get very much reduced wave drag. So that's why if you can sweep your wings in, that's a good idea. And you can see here, this particular, you've got ones here, you can see the shock wave here, and there's actually put inside at 30 and 45, this sort of thing. You make sure it goes inside. Sometimes a boom is put on there in order to control, shall we say, and keep it away from the actual fuselage, and also to control the angle that you want. You can see here, you've got a cone there to actually intake air. But this part here has made sure the shock wave is out here, not on this particular part of the body. So any air intake going in through here would be a much different speed than if we didn't have that boom in place. And therefore you can see different sort of sweep actually activating in what's going on here. Okay, and then we get up to the real fast ones where we've got the ramjets and the scramjets. So ramjets, we're travelling supersonically, but we're taking air in, we slow it down so it's subsonic, and then we actually burn it. Scramjets, not so many of them around, but they travel supersonically best. They take in supersonic flow. When the flow is still supersonic, that's where you combust it. So therefore a very different and a very highly demanding type of event in order to get as much energy out as possible. So this is why these are still very much in development, a lot of work, research being done on these. Ramjets have been around for quite a while. Okay, and I think that's about it on that one.